So for this first problem, it's number 10. You have an urn that has 7 balls in it, and they are labeled 1 through 7. 3 of these are going to be drawn successively without replacement. That's important. And they'll be placed in a row in the order they're drawn to form a 3-digit number. Order is important here. So find the probability that this number is strictly less than 320. Well, first of all, let's go back to order is important here. The difference between a permutation and a combination is that permutations take into account order. In other words, drawing the numbers 2, 3, 1 is different than 1, 2, 3. In a combination, they don't make that distinction. Since we're looking at the value of the number, we do need to take that into account. So now let's talk about finding the probability of a number that in this case is less than 320. So that probability is going to be calculated by taking the number of successes, the number of numbers that actually fall into that category, and dividing it by the total number of digits, or numbers, I should say, 3-digit numbers that you could actually create with this method. So for the bottom, to get that total, again, because order matters, I'm going to do a permutation. There are 7 numbers, and I'm going to choose 3 of them. So that's 7p3. You just type that in your calculator, and it will spit out 210. Now for the successes, this is where you have to think a little more. For the first digit, you have the options of a 3, a 2, and a 1. Anything else will not meet the criteria of being less than 320. Now you have to talk about the 3 digits within each one of those. So you have a certain number of choices for each of the 3 digits. Now, for the 3, the first digit, you only have one choice. 3, you already made it. Then for the next digit, because you can't be greater than 320, you only have one choice, and that is the number 1. The ones I have in these first 2 places is not the digit, it's the number of choices you have. So you only have one choice with the 3. You only have one choice. The next number has to be a 1. You can't duplicate because there's no replacement. So you've already used the 3 and the 1. That means there's only 5 more numbers for that last digit. So 1 times 1 times 5 is 5. For that first number that begins with a 3, there are only 5 numbers that will work there. Now you could start with the 2. That means you have one choice for your first digit. Now for the second digit, you have 6 choices. All the choices but 2 are still available, but the number 2 are still available. Once you make that choice, for the third place, you only have 5 choices. So 1 times 6 times 5 is obviously 30. Now, if you have 1 as your first number, again, in that first place, you only have one choice. You've chosen the number 1 there. Then you would have 6 choices available after that, and then 5 after that. So that would give you a total of 30 also. If we add those all up, we get 65. So now if we go back and plug into our formula, the number of successes is 65. The number of the total numbers that we could create is 210. And then we can reduce that. 65 and 210 are both divisible by 5. So you're going to get 13 on the top, and you're going to get 42 on the bottom if you reduce there. And that is choice C. So that would be the answer for this one. So this next problem involves choosing 2 cards from a standard deck of 52 cards, and they tell you order is not important, and we're doing this without replacement. So what is the probability that Gretchen would choose 1 king and 1 queen? So again, we're going to look at the probability of a king and a queen. I know order isn't important. I just put it king, comma, queen. And that equals the successes over the total. Well, the total is just going to be 52 choose 2 because there's 52 cards and we're going to choose 2. The top numbers now, we just have to look at a king and a queen. We don't have to worry about any overlap there. You can't be a king and a queen. So the first choice would be a 4 choose 1. And the second choice would also be a 4 choose 1 because there's 4 kings, you're going to choose 1. There's 4 queens, you're going to choose 1. And so that means that choice A is the correct answer here. So number 16 asks you to consider an experiment where 2 fair 6-sided die are rolled. Let x be the maximum of the two numbers that show up. Find the probability that x is greater than 3. So I went ahead and snipped in for you a little diagram that shows the possibilities when you roll two six-sided dice. And it makes sense, that you would have 36 choices here, right? 6 times 6. And so you might say, well, how am I going to count up all the ones that have an x value greater than 3? What I would do here is instead I would count up the number that have an x value less than 3 and just subtract it from 36. So you can see I've boxed those in purple. And even if you didn't have this little chart with you, you should just remember that there are always 36 possibilities when you roll two six-sided die, and then know that you could just very quickly think about, okay, I have to be 3 or less, and then subtract that from the 36. So I could pair a 1 with a 1, a 1 with a 2, a 1 with a 3. I can pair a 2 with a 1, a 2 with a 2, a 2 with a 3. I can do the same thing with the 3, pair it with a 1, pair it with a 2, pair it with another 3. And I can quickly see that there are 9 possibilities there that don't work. So 36 minus 9 is 27. That means there are 27 possibilities that do work, and there's a total of 36, right? So it's always successes over your total. Well, 27 and 36 are both divisible by 9. So if I reduce that, I'm going to get 3/4, and that would be choice A. So this is how I would do number 16. So this is an expected value problem. Alice is playing a carnival game, and it costs $3. Then she's going to follow some rules that are set out, right? So she's going to roll a fair die, and if the number shows up odd, then Alice gets that amount of money. So for that, I did 1 out of 6 times 1 plus 1 out of 6 times 3 plus 1 out of 6 times 5, because those are the probabilities and the amounts of money that she would win for rolling a 1, a 3, or a 5. Now we're going to add to that what would happen if she gets an even number. Well, the probability of her getting an even number is 3 out of 6, or 1/2. And then she's going to toss a coin. And if that coin comes out heads, which again would have a probability of 1/2, then she gets $5. Now, if the coin toss results in a tail, then she gets nothing. So I just put a +0 there. And we do have to remember that she also paid $3 to play the game in the first place. Now, if you wanted to, you could convert everything to decimals, but I dealt with the fractions because I want to get as close to the real answer as possible, and I don't want to round. So if I add up the 3, the 5, and the 1 out of 6, I get 9 out of 6, and then plus 5/4 there. And then I'm going to subtract a 3 from that. So I just found a common denominator. I reduced the 9 over 6 to 2/3, or 3/2, excuse me. And then I doubled that to get it over 4 so I could add it to the 5/4. And then I subtracted 3 from that. Again, you could do this in your calculator. When you do the math and it's all said and done, you get that she actually would expect to lose 25 cents by playing this game. So for number 19, they tell you that every time Alice takes a bite of the Eat Me cake, she grows taller by a random number of centimeters, which we're going to refer to as x. Now suppose that x can be modeled by a normal distribution, and I've given you a little visual for that. I snipped in the normal curve. And they're telling you that the average score is 70 with a standard deviation sigma of 12. You're asked to find the probability that x falls between 79 and 97. So just to give you a visual, guys, this won't actually enter into the calculation, but if you look at a normal curve, what it looks like, we're looking at values between, say, 79, and 97. So I'll just shade it in like this portion right here. So we're trying to find the probability of that portion of the curve. And so what we're going to do there is we're going to do a z-score calculation for both 79 and for 97, which is a very straightforward calculation. It's always the value you're interested in, which is 79 or 97, minus your average, which is 70 in this case, divided by your standard deviation, which is 12. So if you do the math there, for the first z-score, you'll get 0.75. And then for the second z-score, where 97 is your x value, you get 2.25. And I've shown my math there. Then you have to use the chart that's attached to the back of your Notre Dame final review. And if you look at the number, the value under A that's associated with the z-score of 0.75, you get 0.2734. And then for a z-score of 2.25 in the chart, it will give you a value of 0.4878. And then just subtract. It's always the largest minus smallest. And so when you do that subtraction, you can see that you get 2144.2144. And so the answer there then would be choice C. So I hope this helps. If you need help with some of the other problems, reach out to me tomorrow. I know Mr. Holtz offered the possibility of waiting until Friday to take the test. So if you choose to do that, you can certainly come see me in the meantime. And yeah, just let me know if you need anything else. Have a good night.